So, my lunchtime philosophy talk today is about modeling and simulation. So, we already defined that it's mostly about epistemology of simulation. And this talk is based on my attendance of two conferences in May and April, which I attended for pleasure, and in one of them I managed to get accepted with the talk even. So, and there were two excellent conferences, and one on philosophy of experimentation and the other on philosophy of modeling and simulation. And I heard those discussions, I participated in discussions. I borrowed ideas from there, put together in a talk, and going to share with you ideas which I learned there. So, first of all, the topic of my talk, I'm not going to discuss my talk, it's the least interesting thing. There are many more well-established philosophers in the field besides me. So, but my disagreement with the position, first at a glance, was that people were unclear of what to call simulation, what to call modeling. For example, Eric Wiesberg, one of the very important authors in this field, calls simulation kind of theorizing both construction of local representative models and also experimenting with computer, the second facet of this definition. Also, he calls model itself a simulation of something, and also in his latest papers he calls, maybe earliest also I saw this in the latest, in his encyclopedia paper, he calls one run of a simulation code a simulation. If you run many times, it is a modeling. It's like, but all authors cite one of the first authors in this field, Stefan Hartmann, in his definition. He calls simulation that simulation imitates one process, is an imitation of one process by another process. As many authors agree with this. This implies similarity, because if you build a model of one process by another process, you need good grounds to believe that this another process resembles somehow or is similar to this first process. So another important author here, Paul Humphreys, says about computer simulation. This is exploring of properties of mathematical models, exploring properties, and also a computational device which produces solutions. So exploring properties is kind of study of a model. So we see two parts. First, building of a model, creation, construction of a model, and then study of a model, exploring its properties. So that's definition by Humphreys about the second part. In his new book, Michael Weisberg calls modeling a study of a real-world system via construction and analysis of models. We see also construction and analysis, but in the book by Michael Weisberg, it is called modeling, but Eric Wiesberg calls this the same simulation. That's kind of confusion of, or maybe not a confusion, but a broad use of both terms. They overlap. Also, he calls a simulation computing the behavior of the model using a particular set of initial conditions. This is very close to the definition by Eric Wiesberg when he calls one run the simulation, because computing behavior using a particular set of initial conditions is close to one run. He calls this modeling, and Wiesberg calls this simulation. But anyway, so despite of this absence of agreement on the terms, it seems clear that the practice has two facets: creation, construction of models, and then exploring the models. In my paper, I argued, based on some arguments I'm not going to discuss here today, I argued that it is very important to call creation of models, modeling and exploration of models simulation. And then disentangle many unclear things.
But not everybody following this usage of words, right? As you are saying, the terms are overlapped somehow, and
yes,
different authors are using them differently.
People use them differently.
Can I ask, did anybody make distinction between simulation and emulation?
No, I never heard the word emulation in this series of conferences. So, which kinds of simulation exist? Paul Humphreys discusses 4 kinds. First, it is what I talked about just a few minutes ago. It's computer simulation. It's all, you are all experts in this. And for the computer simulations, some authors argue for a very interesting thing, that Monte Carlo simulations are not genuine simulations. Because what people simulate in the Monte Carlo model is not exactly the model of the process, not similar to the process which is simulated. The example is number pi, for example. They discuss the following thing. If you, for example, simulate the planetary motion at some stage, you need to calculate the number pi. To calculate number pi, you kind of simulate a box, inscribe a circle there, and drop objects or dots, and then count the relative density in this. So you drop the objects in a circle, drop objects in the box, but you simulate the planetary motion. So there's different things there. I disagree with this, because besides this assumption, complementary assumption of calculation pi, you also directly simulate the planetary motion too. But people are very...
This, by the way, giving rise to a very interesting point, the unity of knowledge. You extracting pi from some very specific sort of operations, and then applying it, say, for Gaussian distribution, for age distribution of people in the city, or planetary motion, or whatever. So this is unity of our knowledge, unity of Platonic forms, which is everywhere. Totality of Platonic forms, the same Platonic form.
Yes, but they call this not genuine. But not all people agree. For example, John Norton from Pittsburgh argues that stochastic Monte Carlo simulations are genuine simulations, because they simulate exactly what is the epistemic target of this model. Anyway, second kind of simulation is analog ones. It's like you simulate damped oscillator, like mechanic oscillator, like with the electric circuit, oscillations of electric current parameters in the electric circuit. So damped oscillator, mechanic thing, and electric thing. That's analog simulations. Then scale simulations, well known Drosophila and genetic studies. But the most interesting example is 10 authors discuss this example, this San Francisco Bay model. When a question arose whether dumping of the San Francisco Bay will, because of the dumping, of the envisioned dumping, the water flow will destroy the bay, the US Army Corps built the model, scale model, small San Francisco Bay model, which is shown here on the right, right bottom plot. So this is the San Francisco Bay model. That's scale model because it is a model made of the same thing as sand or water or whatever, but smaller. It's called a scale model. And
What is the scale, by the way, of this one?
Oh, maybe that's
The Bay Bridge is 20 meters wide.
1,000 or
1,000. So it is few meters. The Golden Gate, in this case,
Yeah.
is just few meters.
Golden Gate is 20
Wait.
20 meters.
Huh?
The Golden Gate is 20 meters in width.
20 meters here, you think?
Not here, just that's how wide the actual Golden
Oh.
Gate Bridge is,
yeah.
approximately.
So that's scale. And another important example is agent-based simulation. Agent-based is when you use individual objects to which you ascribe kind of transition rules. Bring them in interaction according to these rules and looks what happens. Example is this chessboard. That's bottom plot. Chessboard. These red checkers and blue checkers represent different groups of people. For example, smokers and non-smokers. And the percentage here represents the percent of tolerance people to the other group. For example, how many of your neighbors you prefer to have with having the same property that which you have. For example, 30% means that during these simulations, each this checker making a move on the chessboard chooses among the neighbors at least 30% with the same property. Smokers like non-smokers, non-smokers like non-smokers. Simulations, it is called Schilling segregation model. Schilling segregation model shows that at least at 30% of preference of neighbor of the same kind, for example, non-smoker by non-smoker, after several moves, segregation happens. So they differentiate, they occupy different places in the chessboard. So that's an example of agent-based simulation. And in this talk I will concentrate on the first one, which is familiar to all of you, it is computer simulations. There's many others. First of all, what is computer simulations? Paul Humphreys, for example, argues that computer simulations is neo-Pythagoreans, and people who do computer simulations are followers of Pythagoras, because Pythagoras argued that the world is made up of numbers. I put this slide exactly because I heard the discussion here in this seminar previously. So, made up of numbers. And anti-realists agree with this. It is very coherent with anti-realist position, because they say that any consistent theory can be interpreted to be about natural numbers. This conclusion Paul Humphreys takes from semantics, formal semantics, because I will not discuss this here, but semantic specialists argue that any consistent theory, for any consistent theory, all you need is to distinguish between elements, and after you distinguish between elements, you can ascribe natural numbers to them. That's a convention. For example, computer operates on binary states and strings of binary states, zeros and ones. And those strings, on one hand, they are conventions, because actually that's low current, high current is cheap, reliable. But on the other hand, it is a string of syntax, informal semantics, strings of syntax. And computer interprets theory in numerical terms, operating on these strings of syntax, strings of numbers.
Why, Vitaly, why they call themselves anti-realists?
Well, because
they don't need real numbers.
if you're really, you're speaking about something which exists independent of your conventions. But here we see only conventions about numbers.
Mm-hmm. Mm-hmm. So they do not agree that numbers by themselves exist as Platonic forms. They are rejecting Platonic world of forms.
Probably that's a weak form of this argument. There's kind of claiming that simulationists live in the world of numbers.
Mm-hmm.
But that's their only world they exist in.
Mm-hmm.
So maybe somebody's convention, but not theirs. For them, it's everything. So this conventionalist interpretation is suggested also by the statement that the model, simulation model, always contains non-detachable interpretation, because those numbers stem from theories, and theories contain interpretation.
Mm-hmm. Non-detachable.
Non-detachable.
Ah, that's why they are anti-realists, because
Yes.
Platonic
Yeah.
forms are detached.
Yes.
They are detached.
Absolutely.
Okay, clear. Yes.
I think calling these binary states in computers numbers is not a convention just based on the states. It's what you do with them. You do arithmetic on them. You use them to do something that models addition, subtraction, multiplication, and division. They could be used in other ways. For example, if you use them as Boolean objects and do Boolean logic with them, then they're not numbers anymore. They're something else.
That's convention.
Well, it's a matter of what you do to, it's a matter of how you operate on them. Yeah, okay, we can call it a convention.
But this is position of anti-realists of Vitaly is talking us, right?
Yeah.
Not necessarily his position. Right?
But I'm simulationist, so I probably need to agree with this.
Yeah, what I'm saying is, what makes them numbers is not just the things themselves, but how they operate with each other. How you interact, how they interact, they combine to form.
Multiplication.
Yeah, addition, subtraction.
Algebra.
Right. And if you do other things with them, they're the same objects, but they're not like numbers anymore. Anyway, go ahead.
Okay, so let's call it them number. Numbers is a convention.
Mm-hmm. Non-detachable.
Yes. So questions. If this is a philosophy, it means that people ask questions. That's what they like to do most of all. And I just put together here the questions which seem to me the most appropriate. For example, question of accuracy and reliability of simulation. People ask, what justifies accuracy and reliability of simulation? The very close question posed by Deborah Mayo for scientific experimentation, and Parker applied this argument to computer simulations. The question of epistemology is what canonical error can arise in simulation. So question of error in simulation. Another question, what kind of knowledge is acquired in simulation? Because we study kind of real world object or kind of epistemic target, but on the other hand, we actually in simulation, we study the model. And we acquire knowledge about the model. And the question is how this model, knowledge about this model is related to knowledge about the target.
Vitaly, could you say again what do you mean canonical error? Which sort of error is defined as canonical?
Deborah Meyer writes about statistics, statistical approach. So that's statistical definition. But also we can, of course, we can keep in mind any systematic errors.
So the word canonical means nothing in this respect. Could I omit it and the question would be the same or question change? What error can arise in simulation? Or what canonical error? What is the difference between canonical and non-canonical error?
Statistics, reference to statistics.
So canonical is referred to statistics?
Yeah, I think it comes from there.
Mhm.
So another question is, what is, yes, Freak poses this question, what is new about computer simulations compared to paper and pencil? Are the questions the same, or the computer doesn't bring anything new to the table? Is simulation the same as modeling? That's the question I debated. Is theory the same as, is simulation theory or experiment? This is a big question which discusses, for example, which is discussed by many authors, and people reveal several epistemic strategies typical for experiment in sciences, which is applied also in simulation. I will discuss several such examples. Are simulations normative? So are they a must for the experiment? And what is the role of user and expertise in simulation? I will start from the last questions, not the very last, but from the normativity question. First, we all know about the advantages of simulations. For example, we can use simulations when we study complicated objects which are very expensive or cannot be built or like this. But also there is a possibility to make exploration, a discovery in simulations. And one of such examples is discussed that, for example, counter-rotating vortex structures were first discovered in simulations, and only after that they were discovered analytically.
What sort of, sorry, I don't know, could you say a few words, what is counter-rotating vortex structures?
It's kind of a mathematical property of objects which are used, for example, they used for studying planetary motion.
Mm-hmm.
So, but that's kind of mathematical structure,
Mm-hmm.
which was first studied by simulations, and their properties discovered, not analytically, by computer simulations, by Hawley, and only after that, the same year, but later.
Mandelbrot discovered his fractal in simulations, actually.
Good example. Good example. Even more widely known.
Yeah.
Also, another interesting discussion by Emily Park at these conferences was about surprises in simulations. She mostly discussed simulations in biology. Surprises is mostly like exploration or discovery of something, unexpected things, unexpected properties of something.
Again, this Mandelbrot said it's very
Yes,
impressive.
Yes, but that's also in biology and
Yeah.
other sciences. But that's about advantage. There are some disadvantages of this. For example, well-known thing which is discussed also widely is necessary tuning of simulation parameters to various kinds of data. And what does it bring to the table from the point of view of progress in science? Are the simulations a must, for example? And several authors discuss the following interesting example. Kepler discovered his elliptic orbits when he couldn't solve the problem of describing all the available Tycho Brahe's data.
No, Ptolemaic model described it very well.
However, Ptolemaic model described very well, but the question was probably about the amount of data. Describe all data. There were inconsistencies and like this. But if just Friedman, quoted in Humphreys, says the following: just imagine Kepler fits the best circular orbit for Mars by least squares. If he had a computer and least squares, and just fitted Tycho Brahe's data using Ptolemaic orbits, it would be fitted perfectly, and he would not need to put any effort in developing, on thinking about this elliptic.
I disagree, because this consideration completely neglects the real motivation of Kepler. Kepler was mystic and religious thinker. For him, Platonism or Pythagoreanism was a religion, and he refuted this Ptolemaic model not on the ground of poor accuracy. No, it was sort of arbitrary garbage of infinite number of parameters. He believed that the true knowledge is elegant, simple, and beautiful, and he did not see beauty in that. So he refuted it on the ground of beauty, not on the ground of accuracy. That was the real motivation of Kepler. We discussed it here, actually, if you remember.
Yes, I see. It is difficult to argue for and against this because of counterfactuality. He did not have a computer. We don't know what would have happened if he...
Yeah, even if he had, actually, it wouldn't work, because he had completely different motivation.
But you know, there is a point in this, because if he had a philosophical position, he always thought about something. He saw Tycho Brahe's data, and he was thinking about them, applying his intellectual effort to this. Because there was a problem there, and he solved it this way. But if he had a computer, there will be no problem. Maybe there are philosophically thinking people around us, but we have a lot of computers, and everything is solved, but by least squares. So that's a question. That's an argument. Next point about simulations and experimentations. Why at all one needs to use experimental strategies in simulation? First of all, due to complexity, which is also called sometimes opacity of simulations. For example, consider such an example. You have a Monte Carlo code. You wrote it yourself. You know every line. But you have 100,000 lines of the code. In this Monte Carlo, you need to repeat 1,000,000 times this, or several million times. Even if you follow the code line by line, you can do this for one event for a couple of hours. But you cannot do this 1,000,000 times. It is opaque for you when you do a full simulation, all 1,000,000. It is opaque for you. You need to kind of put it behind the sorting curtain and let it calculate something by itself. That's opacity. Another facet of opacity is because for some systems analytical solution is generally not available. You need to use numerical scheme, which is very, very time consuming. And there is a third very interesting argument brought forward by Emily Park during these couple of conferences. She put it this way. She's speaking about a simulationist who runs the code, and which obstacle he or she meets. And she writes, she, simulationist, didn't write the model herself and is ignorant of aspects of how it was programmed and how it works. That's another way of opacity. There's only one thing if you have written the code yourself and you know every line and understand every line and just cannot follow because of time constraints. On the other hand, the other aspect, if you are ignorant of the code, that's the user.
Worse.
That's the user problem.
Yeah.
That's I call this ignorance argument. she also discusses several other examples. For example, she discusses how people work on a complex distributed code projects, for example, maybe big codes in high energy physics. When people work on a part of the code and don't know what's going on in another code, in another part of the code. Or here another example, if somebody writes a procedure on a high level language and doesn't know what's going on the low level. But if we look at all these examples, they can be reduced to ignorance, various aspects of ignorance. That's why I call this part argument as the ignorance argument. Also, she did not write the model herself. It is also not important, it's irrelevant. Because just imagine you read Mark Twain, for example. You did not write Mark Twain, but if you understand the language, there is a question of connotations, hidden connotations, of course, in the language. But if you are a native speaker of the same language as Mark Twain, and you read his writings, you comprehend everything. You don't need to be the author to understand everything. So the authorship is not the argument here. The argument is ignorance or experience. So that's why people need to use experimental strategies. And the most important experimental strategies are discussed by the very renowned author in the philosophy of experimentation, Alan Franklin. One of such strategies are the checks and calibrations, reproducing known results. In an apparatus, you need to reproduce known results. For example, if you're studying whether your electronic microscope works, first you need to see in this microscope exactly the same what you saw previously in optic microscope. If you see the same, you can study new things. But if you didn't see, it doesn't work. Exactly the same simulationists do. Winsberg says, simulationists show that simulation outputs much analytical solutions, that's a separate question, or data from experiments. So simulation first needs to reproduce the data, and after that you can try to believe it. There are more complications about analytical solutions, because for analytical solutions, theories are always underdetermined by data, and any analytical solution has a limited scope of validity, and that's another question. But you also can double check or verify, or is better to say validate your code with an analytical solution if it's available. That's also.
People also sometimes distinguish between validation and verification.
Yes, I will come to this. Yes, exactly. So another approach taken from experiment to simulations is to vary a parameter and see a response. You can play with one parameter and see the response in the outputs. That's the same reproducibility by dynamic, kind of dynamic. Like adding ink to this or that ink to a sample and looking in the microscope how the ink changes. That's what experimentalists do in biology. You can do the same in simulations. Then measuring the same observable in different kind of apparatus. That's in experiment. For simulationists, it's the same as to calculate, to simulate the same observable using another code. Why do you need another code? I will discuss it in my next slide. So, but before coming to verification, validation, and this last strategy about different codes, let's discuss what you do in simulations and what philosophers say about this. Building models and studying models, you very often do what you call simplifications. Okay, you get rid of details of bolts or some smaller details or dust or air or whatever. And there are two people distinguish two different kinds of operation here. First is abstraction. Abstraction is the elimination of one of the properties, leaving others invariant, unchanged. You can do this by three ways. First of all, you can leave your parameters, which you are going to eliminate, existing, but just cognitively ignore them. For example, an example by Humphreys is that a piece of radioactive uranium, it emits alpha particles. But if you don't need this alpha particle, you can just ignore them and simulate as if it is just a piece of this type of nuclei without taking into account this decay properties. And second approach is setting your parameter to 0. You have a code for this, but you just set it equal to 0. And this is called representational abstraction. Mm-hmm. And the third way is the physically eliminate. For example, if you are producing in your system a lot of, I don't know, neutrons are produced, but you don't need these neutrons. You need everything else in the model, exactly the same, but you don't need this amount of neutrons. You cannot delete the code. You cannot set it equal to 0, kill neutrons in the code. But you need to eliminate them somehow. You can put in the room somewhere a brick of boron, for example, a fake brick of boron. Boron will absorb all the neutrons. Mm-hmm. So that's physically eliminated. Mm-hmm. And another way is the idealization. Idealization is transforming of property into another which possesses desired features. Mm-hmm. So speaking about density of air, for example, you can, if you the abstraction, if you set it to 0 or delete or remove air, but if you need air but a different density, for example, you set or different chemical composition, you just set this feature to your desire. There's cognitively different procedures. Their example is treating planets as spherical. That's the idealization. Okay, so, but which problems arose also in simulation when we do this abstraction and idealization? One of the most prominent issues is the Duhem-Quine problem. Duhem-Quine thesis says that any theory, a simulation is based on theories. Any theory is embedded in a network of auxiliary assumptions, any of which can fail, and the statement of epistemic holism, holists say that all these assumptions or all theories so interrelated and so entangled and interlaced so that you cannot disentangle. If something goes wrong, the theory is so much interrelated that you cannot distinguish what exactly is wrong. Mm-hmm. This is a strong argument. This is an old argument because it's holism. This is a strong argument, but it can be dealt with. but special techniques are necessary. People discuss how one can deal with it. It is not easy. For example, it was discussed in my talk. But one of the examples of this holism is the procedure very often used by simulationists, which is called discretization. The example is the following. It's not example, but it's better to say definition is the following. Physics systems are described by systems of differential. The climate models. And some of the first climate models began to fail, to blow up, because they worked fine first few days. And after that, code started to require almost infinite calculation time. Just blew up, you can't use it. Another important issue here is, imagine the model doesn't fail. Your simulation model, which consists of underlying theory, of assumptions, of discretization, of everything, it doesn't. If it fails, you don't know what to blame. But if it does not fail, why it doesn't fail? What is possible is the balance of approximation. Balance of approximation. For example, maybe this, Lisberg calls this piecemeal adjustment. This may be adjustment piece by piece. Maybe theory is not very good for this amount of data. But you add so many assumptions, free parameters, schemes, discretization, or whatever, that in total they fit the data well. That's another side, yes. Tweaking with parameters. That's another issue. And exactly this is the problem that creates a problem for verification and validation I've discussed. This is verification and validation, and they are the epistemic strategies for simulations. First you need to verify the model code, then you need to validate. But some authors argue, for example, Jebel in this conference, argues that verification and validation, because of these discretization issues with examples, are entangled.
Would you give a definition first of what is called verification? What is called
Next slide. So that's another side. You cannot disentangle the theories. You can disentangle what goes wrong. But what can go wrong? I argue that this problem is solvable. Technically solvable, but some efforts are necessary. But it's not about my argument. So what is verification and validation? How are they entangled? The definition, standard of an American standard in this field, says that the process of determining that a model implementation accurately represents the developer's conceptual description of the model and the solution of the model. So, Oberkampf, an author and a physicist in the verification and validation, says that, puts it this way, verification deals with mathematics. That's the practitioner's point of view. Philosophers argue that not everything that's simple. There are two things to verify the code. First, the code verification, which includes fixing mistakes in the code, and solution verification, estimation of error and accuracy of inputs and outputs. That's all verification. And argued that verification, if we define modeling and simulation as I do, they are disentangled, because verification is exactly relevant for modeling and validation for simulation, but no, not about that argument. So that's what verification is: code and solution and validation. The definition says that the process determining the degree to which the model is an accurate representation of the real world. So this discusses real world. And Oberkampf says that validation deals with physics. Verification with mathematics and validation with physics. So it determines, validation determines relation of the model to experimental data. And so analytical solution for such a system, not generally available. For the verification stage, analytical solution, if you kind of disentangle, if you kind of study piecewise your model, elementary model one by one in your code, you can verify it using analytical approaches, analytical solution piece by piece. That's for verification. But in validation, if you validate the entire model, the entire your accelerator, or maybe not a good example, but big experimental setup, analytical solutions for such a big thing are not available. You have to start validation and compare and check the relation to the experimental data, exactly as experimental practice, as you validate your device, huge models. Another, based on verification and validation, approach, which is also used in experimentation, is calibration. And calibration exactly involves model tuning. When you calibrate, you tweak the parameters so that they describe a set of data to which you believe. So that's what calibration does. And in this definition, it exactly poses the problem, the DUM problem for this. Which parameters do you tweak? If you tweak arbitrarily any parameters, if you are ignorant of the physics model in the ignorance argument, you can tweak any parameters just so that to describe your set of data very well, not taking care of what goes going on with other data, with all data, just this part. And okay. So, and calibration is an experimental strategy. That's why the verification and validation should be disentangled. For example, you have a model of Maxwell equation, and you have a model of accelerator ring. And you're trying to reproduce some data measurement for an accelerator, and your model doesn't fit it well. You're trying to tweak parameters. If somebody tweaks the parameters of the Maxwellian equation to describe, that's exactly creates this entanglement between verification and validation, because you verify your code line by line, equation by equation, and validation is the big system and big data from a big experiment. So That's problem for calibrations. And now my summary. I'm almost exactly in time. So, this because of the Duhem-Quine problem which we discussed. The practitioners claim all the same type codes are the same, just cross sections are different very often. Or all codes have to do the same, have to yield the same results. This statement, this claim is false and irrelevant because they don't take into account assumptions such as discretizations, with which every model is overfilled. Assumptions, discretization in different simulation codes can be so different that, I quote Lenhardt, run counter the underlying theory and experience. An example, Arakawa operator. Any big code has such a Arakawa operator. Not literally Arakawa, but
simplification.
Like this, yes. Also good example. So, and measuring or simulating the same observable in different kind of apparatus, this is a Franklin strategy, experimental epistemic strategy of experiment, can be a remedy for this. Using different codes. How? Whose Arakawa operator is better? You don't know if you don't try several codes with different schemes, different assumptions to describe the same data. And example, all accelerator codes are not about Maxwellian equations, exactly as all high energy codes are not about QCD, not at least not only. They are all about assumptions. And a suggestion based on this. A detailed, I would say line by line, documenting and commenting of each code is a necessity to avoid what? Black box experimenting, entailing verification, validation, entanglement, and tweaking whatever parameters are. Imagine two people tweak parameters to describe the same set of data. One of them is not ignorant for some reason, and he tweaks validation parameters. The other is ignorant and finds a way to tweak Maxwell equation parameters.
Change speed of light, for
And
instance.
they can, imagine, they can describe the same set of data equally well. Who is right? Can we use his or his code or her? We need this to contend the ignorance opacity problem posed by Park in this conference. And all attempts, my final statement, assertion, all attempts to invent one universal simulation code for a complex epistemic target is all your eggs put in one basket. That's all.
Okay, questions?
So different code has to be based on different principles if you want to compare the two. If you have one simulation, or if you have one simulation that you want to check the validity of, and you compare two that simulate the same thing, then you can't just compare two programs that are based on the same principles, because the principles themselves could be wrong. So couldn't one argue then that simulation reduces to theory anyways?
Simulation is theory-laden, but theories are different. This argument is that assumptions, supplementary assumptions, they are also theories. Most of people speak about the underlying theory. High energy physics is a code about quarks. Accelerator code is about Maxwell, but they are not only about a lot of theories, and they are exactly theory related. And you don't know what to blame because they are entangled in the code.
Okay.
So actually, simulations, all the problematics of simulations is related to creation of new reality. The codes sort of are adding the new reality to the world. We have physical reality, we had Platonic reality, either you accept it or not, but we
Yes.
at least could consider it as a possible way of thinking, very respectable way of thinking. But codes are adding in our world one more one more reality, this reality of codes. And in a sense it is similar to physical world, in a sense similar to Platonic world, in a sense similar to mental world. So it's sort of mixing world, and we should probably realize that this is one more world in this entire big world world of worlds.
Exactly about this, the question posed by Grune-Janov. What kind of knowledge is acquired? About which world? You are studying the epistemic target, but you create another world and study it. What do you study?
Yes.
How do they relate?
That's one more big set of questions about relation between all these worlds. Mental world, Platonical world, physical world, and now simulational world. They all are entangled with each other, and you, with the help of this simulation world, you have more questions than before.
Yeah.
Yeah, but we made the entire world of worlds more interesting. I think this is a point. Good point. We
But
added some.
none of them is more true.
So what is truth? It is one. The question about truth, it became even more complicated than before.
We are creating realities in which
Yes.
we
We
believe.
creating our own reality, and what is the truth about this reality?
Yes.
Yes, I think it's very interesting subject, and
But how does, from a practical, I mean, we worry constantly about benchmarking codes, one code against another. We worry, I've spent 30 years worrying about the assumptions that go into codes that people use, like a black box.
Mhm.
And it's just basically a lot of work. And yeah, you can have some documentation, but then you have to read the documentation.
and
And you
understand.
have to understand it, right? And you have to understand that if you use an electron code, that generally speaking, electron people assume that they're always traveling at the speed of light. And so in one part of a 100,000 line code, there's an assumption that you're moving at the speed of light. And if you try to use it at low energy, all of a sudden that one line breaks the results. It takes a lot of work to find out what the heck is going wrong when something goes wrong. Now, I'm not against philosophical discussions, I'm not against philosophers looking at these problems. Fine, but do they bring something to the table that we can use from a practical point of view to make our jobs easier or more, more organized or something other than the way we do it right now, which is basically just working like heck, trying to make sure that everything is working properly. What I'm asking is, do these philosophers bring something to the table that adds something to what we're already doing?
I think that philosophers discussing dual quite problem in the Rakava operator thing and so on, they help us understand what we do. For example, what should we do to disentangle, of course not practical things, but generally, we need to disentangle verification and validation. We need to document each code and make it and understood to outside reader, not only to people who made the code. For example, just imagine what is for on the practical side for this. What do you problem says, and expertise problem and ignorance problem? That if somebody says, I made a great code, and code fits the date, and then this guy finds another job. Take my code and use it, and nobody can use it.
right.
because it's all about assumptions. It's not about Max.
Right.
Oh, you Max, you know Fortran, take the code and program it further ahead. You can, because this is a problem of assumptions. Everything should be described, not only described in very detail, but also explained to outside user. Outside user should accept or say, now
But I'm
I
telling-
understand
Yes, but
what
it's
you
also
do.
true that outside users very frequently don't want to know all those details. They just want to use the code and get their
If
answers
people
and
don't
move on to the
want
next.
to do something, philosophers can do nothing about that. Even
Yeah.
politicians can. But
I mean, you can write
what
books on it.
philosophers can do to explain, and then you make your choice, or either spend time or not. You have freedom of doing that, but philosophers help you to understand.
I think that actually philosophers are not even trying normally to solve the problem of practitioners. It's a problem of practitioners to solve their own problems. But philosophers are trying to understand in general terms what actually happens, is reflection. What happens? What is the simulation? What is the meaning of this? What sort of the world we are creating?
So they're looking at what people do and describing it. and
Like
or-
animals in the zoo.
and organizing their descriptions in sort of
Like animals
at a
in
higher
the zoo.
level.
Well, they develop language for us.
They developed language, yes, language. For instance, that all sort of words which we heard today,
Yeah,
Yes.
like the distinction between verification and
distinction,
validation.
verification, validation, ignorance, problem, and so on. So they're given the language of reflection on what goes on, because in every practical case you have specific practical situation, and to describe it properly, to understand what happens, you need general words, general terms. And they're trying to invent and to suggest, maybe unsuccessfully, but it's
okay,
still needed.
I understand. But what you're saying then is just, we sort of continue doing what we're doing.
Exactly, they are not going to solve our problems, no. That's for us. But at best they could help us to understand what happens.
What is the function of philosophy, professional philosophy, not what I'm trying to do, probably actually, but it's normativity. They create norms. They explain, debate what people must do, what should be done. Then they can make this known to DOE, to anyone. You should do this. If that's well reflected, it's helpful. If they really understand what's going on, it's very helpful.
For instance, the question, are simulations normative for contemporary experiment? To what extent simulations are normative? This is a question.
Yes, this
It's
is
a
a question.
philosophical question.
Margaret Morrison, I heard in April, Margaret Morrison saying that she considered experiments in CERN and showed on her slide the physics list from Jan 4 code, and she said that simulations are a must for experiment. They are entangled. People who measure
Yeah.
Higgs boson, they always do simulations. And the question if they must or not. For example, question of Kepler. What if people didn't have simulations? Maybe they would create it not. They would discover not Higgs boson but some other boson if they didn't simulate it. Who knows? That's the question. Yes.
Yeah, when you think about, when they do their cuts and they tweak the parameter, and there's a lot of parameter tweaking that goes on in Monte Carlo simulations for high energy physics, a lot.
Yeah.
And is all of that valid? Is all of that, or, can they get any result they want? To answer that question, you have to be an expert on it. You have to actually do it and be an expert. You have to trust the people, because there's a lot of personal expertise and understanding, and even the people who do QCD, the lattice gauge theory guys, will tell you this. There's a lot of tweaking that goes on in doing their lattice gauge calculations, and some of it is science, but some of it is also art and just having a feel for what kind of approximations are good. Now you try to justify that feeling that this is a good approximation. It's tough, and the final answer is, I've spent 20 years working in the field, and I understand what I'm doing.
Mhm. Yeah. And when the code is hundreds of thousands lines, it becomes more or less black box for everybody, even for authors.
The ignorance is a big problem.
Yeah.
Even for authors, nothing to tell about users.
But they,
I'm forgetting when I wrote my code, not even that big. After a while, I'm forgetting what is
Oh,
there.
yeah, absolutely.
yes,
Absolutely.
but if you understand the code, you have a chance to remember. But people not always have a chance to remember
Yes,
because
they
they
don't
didn't know
Yeah.
what to remember sometimes. So that's the question. Until recently, philosophers did not know about the user problem. Only at this conference it was discovered we need to think more about the role of user in simulation. Until recently, philosophers used to think that people writes the code, knows, understands, comprehends every line,
No.
and then uses it like a mathematical tool. What is the problem? Just mathematics. But there are so many users who don't know what's going on in the
And how
code.
much, also, let's look at the mathematical problem. We use mathematics as if we really understood what the real numbers were and how they operate with each other and so forth. And we don't, so many of the times, people use mathematics and they don't understand what the limitations are of even the equations. Like, pushing I don't know, I can think of a good example, an array function past its convergence limit or something like that. I mean, you see it happen so many times. People will use a function assuming that everything's fine, and then you look it up in Abramowitz and Stegen, and you realize, oh my goodness, I'm beyond any point where this function makes any sense.
Maybe this means that actually there is a limit on the length of the code, because we are not able to understand, to comprehend, and to control our codes if they are longer than something, and then they are becoming black box for everybody. And then how could you trust them and rely on this so-called predictive black box, because you really already do not know the relation
Yes,
between
yeah.
input and output, and it cannot be used then. So it means that even if you have extremely powerful computers, the code should be small
this-
enough for to be
Well, there is
transparent, at least for the
benchmarking.
author.
Yeah, nothing is gonna work under all circumstances.
Yeah.
But we need epistemic division of labor. That's what
You can't,
she discussed as a problem of big codes. One person writes one procedure, then they communicate and believe each other.
Then again, believe to what extent we can believe each other. I
As
can
a
believe myself.
whole, it can be only, this code, the entire code can be only experimented with. As experimentalists, exactly.
there's a classic example of this made about a couple of decades ago when the mathematicians classified all the semi-simple groups. And there was a proof. All of a sudden, you have a classification of all the possible semi-simple groups. But no one understood the proof. Different kinds of people understood different pieces of it. Plus, at the very end, someone had to write a program and run through several hundreds of thousands of final examples to make sure that those groups were also not semi-simple. So at the very end, there was actually had to be a computer program written. And then the question became, well, how do you know the computer program is correct? So then there was a huge argument, has this been proved or has it not been proved?
Yeah. And this was exactly
When nobody understands the proof.
This was exactly the case with the Fermat theory when it was first proved by Andrew Wiles, if you remember. He proved this, and it was even in an article in the New York Times at first page. Fermat theory was already proved, and then somebody, I forgot the name of the guy, he realized that it was a mistake.
Yeah.
And then it took time for community to realize that it's really a mistake, and then Andrew Wiles
So there's
proved
always
it again.
checking, cross-checking, and,
Yes,
yeah.
they converge somehow, but
Thank you.
thank you. Very good talk.